Hello and welcome. In this video I will talk about what is a hash table, what's the point of hash table, why we use it, collision resolution strategies, and finally I will do a summary about all of these things. So what it is a data structure to implement associative arrays by mapping keys to values. Internally it uses an array and it has a hash function to generate an index of that array. Okay, so you can see an array that is inside of hash table. Imagine that you have a person and you want to insert the person in the hash table, in the internal array of the hash table. So we take the name as the key, the entire person is the value, the name, the key goes to a hash function, and the hash function generates a code, hash code. This code is the index on the array where we will insert our person. So what is the point of a hash table? We have already arrays and we already know that a hash table have an array inside. So what's the point, right? Well, let's see these. We have indices. In arrays they are sequential. In hash tables they are based on hash keys. In the insert operation, the cost is 01 in arrays. In hash tables is 01 too. So we didn't add any gain, and also we have the star that says in some implementations when the hash table becomes full it have a big loss in performance. Okay, so sometimes it can even be worse than arrays. Okay, at this point we don't have any advantage, right? Let's see the search cost. In arrays they are on because you have to search in the array until we find the right element that we are searching, and if the array doesn't contain the element we have to scan the entire array. In hash tables is 01, is almost direct. The delete operation is on for arrays, and hash tables is 01. And now we have a double star because delete operation requires a search. If you want to delete a specific element you have to search first and then you delete the element. So why we use hash tables? Well, I already gave you the answer in the previous slide. It's because a hash table is very efficient for doing searches. Okay, it is widely used in databases. So let's see these. We have a array and we have hash table. Also we have a person that is at index 4 in the array, the same thing for the hash table, and now we want to search for Tom. Okay, the person here. In an array we go to the first position and ask Tom is here, and no. So we go to the next position and Tom is here, no. So we go to the next, we go to the next, and finally we find the person. Okay. In the other hand, in the hash table we give the name Tom to the hash function, and the hash function generates the number 4, the index in the internal array of the hash table. So let's talk about collision resolution strategies in hash tables. Unfortunately, hash functions can return the same hash code for different keys, and this is known as collision. Okay, when we have different keys that generate the same hash code. We cannot avoid this, so we have to live with this problem. Okay, so there are two main strategies for this. There are more, but I will just talk about two. The first one is the closed addressing, the second one is the open addressing. To make things difficult, closed addressing is also known as open hashing, and open addressing is also known as closed hashing. Okay? To make things even worse, closed addressing is also known as separate chaining, as a third name. Okay? So you can imagine things like this. The princess says, I will use a open hashing. Then Donald Trump says, did you mean open addressing? And Mario says, she is talking about closed addressing. Trump says, what? it's not closed hashing, and the princess finally says, no, it's separate chaining. As you saw, communication can become difficult too between people. So for me, closed addressing doesn't say anything. Open hashing, I don't even know what this means, and I don't care. And separate chaining at least give me a clue. We have a chain that is separated from our hash table, okay? Chain separated from hash table. This scenario, we don't have too much options, okay? So I will choose addressing in the open, okay? So we are addressing in the wide open. Everyone can see the addresses. Something like that. I already said that there are many strategies, okay? And now I'm saying that each strategy have many variations, okay? So each strategy have more options, and this is a very complex topic, and I will not talk about all of them, just a few. So let's talk about separate chaining. Each slot contains a link to another data structure, for example a linked list, a chain that is separate from our hash table, remember. The linked list contains key value pairs with the same hash code, so elements that generate the same hash code goes to the same linked list, okay? When we have collisions, we search in the linked list for the key value pair that matches the key that we want to get. So we have a linked list with elements that generate the same hash code, but they have different keys, so we must search for the right key, okay? The downside of this, it requires additional memory for the structure, the additional linked lists, okay? Let's see this visually. We have a hash table, we have linked lists, and we have people. Tom and Tim generate the same hash code, so they go to this linked list. Ben and Bob generate the same hash code, and they go to this second linked list, okay? What about open addressing? Well, each slot contains a key value pair, but when we have collisions, we have to calculate another index. For example, we get the key, we add 1, and then we get a new hash code. If the new location is free, we insert the element. If not, we have to get the key again, add 2, and generate a new hash code, and then do the verification again until we find a free slot, okay? This technique is known as linear probing, okay? Linear probing. The downside of this, well, when we run out of space, out of empty slots, it becomes difficult because we have to do a lot of calculations like this one. We have to calculate again and again and again and again until we find a free slot, okay? Let's see this visually. We have a hash table and we have people. Tom and Tim generate the same hash code, but Tom arrived first, so he goes here. Tim goes here, but Tom is already in this position, so we generate a new hash code and Tim goes to the next position. Ben and Bob is the same thing, but Ben is in the last position of the array, so Bob goes to the first position of the array, okay? It's just that. So let's do a simple comparison. About collision resolution, separate chaining uses external data structures. Open addressing uses just the hash table, okay? About memory, we have a overhead in separate chaining because we need external structures. Open addressing doesn't have any overhead. How many items can we have in each of them? In separate chaining is virtually unlimited because linked lists, if you have implemented with linked lists, they can grow and grow and grow. The limit is this hardware of your computer, how many memory there is on your computer, okay? In open addressing, If the hash table is 10, the size of 10, it means that the array inside of the hash table has 10 positions, so the maximum will be 10 elements, okay? About removing items, in separate chaining we don't have any problem, but in open addressing it requires a dummy item. What this means? Let's see. We have a hash table and imagine that all the names in the hash table generate the same index, the number 0. So we have Bob, Tom, Tim and Ben. Okay, now imagine that we want to find a guy that is named Bud and the index is 02. So we go to the first position. Is here? No. To the second? Is here? No. Then we go to the third. Is not here. We go to the next position. Is not here too. We go to the next and now we find null. Null is a mark you can see as a flag, for example, for us to know that the search has ended, okay? There is no way that this guy exists on the hash table, okay? Now imagine that Tom was deleted. This position is null again. And now we want to search for Tim. So we go to the first position and is not Tim. We go to the next and we find null. And this is our mark to know that the search has ended, okay? And Tim is here, we miss it, okay? A workaround for this is using a delete item, a dummy item. So we go here to the first position, is not here, we go here, oh, we find a dummy. A dummy means this position is free, but if you are searching, continue search. So we go to the next position and finally we find Tim. Next and finally, about the implementation, separate chaining is simple. Open addressing can be tricky because it requires some workarounds like this one. Okay, so let's review some topics. A hash table is a data structure that contains arrays and the main goal is to provide fast access to data. Okay, is just that. It is used widely in databases where you have thousands and millions of records and you need fast access to data. Okay, the main strategies for collision resolution are separate chaining, that requires additional structures and memory, but they are more efficient when full and they are simpler to implement. And we have a second option, open addressing. The performance decreases a lot, but a lot, when it becomes full and the implementation is tricky, but the data is stored in the actual array, which means it is faster than accessing external structures, like in separate chaining. Okay, so if the hash table is not full, the open addressing is cool, okay, but when it became 70% full, separate chaining gains. So this is the end. And as always, thank you for watching.